I hope everyone's doing good this evening. I am Mr. Ish. Thank you for joining me. In this video, I'm showing you a very interesting improper integral. I will show you this by means of two different ways. In one way, we're looking at it in a generalized manner. In the second approach, we will show you how you could do it in a more easier manner. Our setup is this hyperbolic cosine. Hyperbolic cosine. It has an intercept here at 0, 1. Now what we do is we bring in a hyperbolic sine. The graph looks something like this. This right here is my sine hx. If I am saying let's evaluate the area between 0 and infinity, what does that include? 0 up to infinity. Here's the intercept for hyperbolic sine. Here's the intercept for hyperbolic cosine. But then you're looking at all of this area right over here because you're looking from 0 in that direction towards infinity, the area between the curves. If you were to blow this out or zoom it in, you're seeing the hyperbolic cosine is like this, but the hyperbolic sine very much shares, and then this right here is the area. You have an infinitely small space here between the two curves, and hence you will expect convergence to occur. But again, I'm going to show you this in the first method, the more harder approach. The second method, the more easier, efficient approach. Your integral is what? It's going to be this, your top boundary curve, which is hyperbolic cosine, and your lower boundary curve, which is your hyperbolic sine, and then dx, you're looking at from 0 up to infinity. If you want to formalize it, you can say limit as t approaches infinity, and then this can be a t over here. And this is a type 1 improper integral because the limit does exist. Your function is not these individually. Your function is basically hyperbolic cosine x minus hyperbolic sine. That right here represents your function. If you do limit as t approaches infinity, this limit exists, hence it's a type 1 improper integral. The antiderivative here is a sine hx. The antiderivative over there is a hyperbolic cosine. You're looking at it from t and a 0, limit as t approaches infinity. What you would do is put t in places of x, then you put 0 in places of x, and the difference. You would have hyperbolic sine ht minus hyperbolic cosine t. This is your upper limit. Now we'll put in the lower limit. Hyperbolic sine 0 minus hyperbolic cosine 0. This right here is equal to a 0. This here is equal to a 1. You have to evaluate these. You're bringing in an infinity. What you would do over here is break these down into their specific definitions. E to the x minus e to the minus x over 2 minus e to the x plus e to the minus x over 2. You can eliminate these over 2's because in the face of this infinity, 2 is meaningless. And you can bring in your infinities or your t's because t here represents infinity. I'm just bringing in infinity, and that's what I have. Don't forget to parenthesize this because the minus impacts this entire definition. This e to the infinity and minus e to the infinity cancel out, but you have a minus e to the minus infinity minus e to the minus infinity. These are equal to 0 because you are essentially looking at 1 over e to the infinity. There's a minus 1 over e to the infinity. These are equal to 0 individually. 1 divided by an exceedingly large number is 0. You have a 0 minus that minus 1, and your end result is 1. This area between curve over here is equal to a 1, this entire shaded region. But this here represents a more difficult approach. There's a more easy approach. It's your efficient, your common sense approach, and I'll show you that next. When you've established that you're looking here at a type 1 improper integral, bring in your definitions here and see what happens. Limit as t approaches infinity. You have e to the x plus e to the minus x over 2 minus e to the x minus e to the minus x over 2 dx. All you have to do is simplify this part right here. You have everything over 2, and let's simplify. E to the x plus e to the minus x minus e to the x plus e to the minus x. These will cancel out. You'll end up seeing 2 e to the minus x over 2, which is equal to e to the minus x. This becomes your function. Your simplified function becomes e to the minus x. Now if you look at it, limit as t approaching infinity, e to the minus x is a limit which exists because it's equal to 0. It's a limit which exists. Now what have I shown you here? I've shown you this entire integral can be written by means of that algebraic simplification as this, e to the minus x dx. Now if you were to graph it, what are you looking at? You're looking at a graph which looks like this, and from 0 up to infinity, you're looking at an area between curves which is all of this, and obviously that will be convergent. We've already determined we have a convergent value which is 1, a finite value. Do the antiderivative. You have e to the minus x divided by minus 1. But this minus 1 can be written in a better way. You can just bring the minus right over here and then you have here from t and 0. When you do the upper limit, lower limit, it's easy. You have minus 1 over e to the t minus 1 over e to the 0. If t is equal to infinity, this zeroes out. If e to the power of 0 is evaluated, it's equal to 1. You have minus 1, which is equal to a plus 1. Again, this area is determined to be positive 1. Here you're seeing the area between the curves is equal to 1. Both of these ways are good. This representation is good. This is your generalized non-efficient approach. This representation is good. You've algebraically simplified and manipulated this into this easier function right over here. And this is the representation of that, but it's an improper integral type 1 with a finite convergent end result. Have a good day. Bye.